Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we'll be continuing with our examination of the derivatives of carboxylic acids, and we're going to begin by looking at the carboxylic acid derivative amide. Now, amides result from the reaction of carboxylic acid derivatives with amines. They represent a very important class of organic compound and are found both in nature as vitamins, amino acids, peptides, enzymes, and synthetic materials such as the polymer nylon. I've drawn the structure of an important vitamin here, nicotinamide or niacinamide, which is a B vitamin. It has the amide functional group. And so amides are very important molecules, and we should begin by looking at their nomenclature. So, the nomenclature of amides. The IUPAC nomenclature for amides involves taking the parent carboxylic acid, taking the oic acid ending of that carboxylic acid, and replacing it with the word amide. For common nomenclature, only the ic acid ending is replaced by amide. If nitrogen is substituted, then a substituent prefix is preceded by the prefix N. The N locant specifies the location of the substituent as being off of the nitrogen. So if I take a simple carboxylic acid, and I replace the OH, this acid's ethanoic or acetic, I replace the OH with an NH2, I have made an amide. The oic acid gets replaced with the word amide, so this becomes ethanamide. Common name acetic acid, we drop the ic acid, and it becomes acetamide. If there is a substituent of nitrogen, such as in this case, where we have two substituents of nitrogen, I indicate this by naming the substituents, the methyls, this dimethyl, as NN dimethyl. Now, the carboxylic acid, if this N with the CH3s was an OH, would be a methanoic acid. Drop the Oic, becomes dimethyl methanamide. A methanoic acid is a formic acid. So the common name would be NN dimethyl formamide. Okay. How about a case where we have a cyclic carboxylic acid, such as in this case? Well, remember, cyclic carboxylic acids are named as cyclic alkanes, and you add the word carboxylic acid. So this is cyclohexane carboxylic acid. Let's put a complicated amide off of here. So we have a fairly complicated amide now. What do we have? Well, we had cyclohexane carboxylic acid, right? We drop the ic acid, right? Actually, we drop the ilic acid in this case. And we have an amide, and so we say N-ethyl, N-methyl, And we have cyclohexane. Cyclohexane carboxamide. All right. Now, we looked at a cyclic derivative in ester section called lactones. A molecule like this, 1, 2, 3, 4 carbons, was butano 4-lactone. Well, what if we cyclized an NH2? What if there was an NH2 instead of an OH off this, and we cyclized it so that this oxygen was replaced with an NH group. So what happens? Well, cyclic amides, like cyclic esters, they're not called lactones, they're called lactams. And so this would become called a butano 4-lactam. Remember the common name, of course. One, two, three, four. A butanoic acid is a butyric acid. This would have been a gamma hydroxy, but now we had an amine here, so this would have been a gamma. Let's show it. Instead of being formed from a hydroxy, it's formed from an NH2. One, two, three, four. So this is 4-butanoic acid, or it's alpha, beta, gamma, a gamma amino butyric acid is the common name. Gamma amino butyric acid, for a common name, would lead to a gamma butyrolactam. Okay. So, lactams, the equivalent of lactones, and there you have it for the nomenclature of amides. What we're going to do now is take a look at the preparation of amides. And most of the preparation reactions we've already covered. We're going to look at them again, but we've already covered them in the last Scribblecast lectures as reactions of other carboxylic acid derivatives. Obviously, the first carboxylic acid derivative we looked at was the acid halide. Acid halides reacted with amines. Okay, so ammonia, such as NH3, or primary or secondary amines, all can give rise to amides. So if we had CH3, C double bond O, Cl, and we hit this with ammonia, we could get nucleophilic attack on the carbonyl. Move the pi electrons out. Our standard nucleophilic acyl substitution. Now the nitrogen's positive, minus on the oxygen. The pi bond to the carbonyl reforms. Chloride's a good leaving group. We click the kick the chloride out, minus Cl minus. And now we have the protonated amide. Amides are not basic, so this guy wants to lose a proton very quickly. And we can use excess base, amine, NH3 can act as an extra base, grab a proton, NH4 plus, becomes the ammonium salt. Hence we're making ammonium chloride, and we end up with our amide. Excellent. And this is the molecule ethanamide. Now, we could have used amines instead of ammonia. I could have replaced my ammonia here with 2 equivalents of, say, ethanamine. Use 2 equivalents of this, one to act as nucleophile, one to act as base. We'll have an ethanamine here. We'll go all the way. We'll end up with an ethyl off of our N. Notice this lone pair on the nitrogen. Okay. In this case, our ethanamide now is N-ethyl ethanamide. And our salt is not ammonium, but it is an N-ethyl ammonium chloride. So there you have it. And of course, we could have used a secondary amine. And if we use a secondary amine, we would produce diethylamine. If we use 2 equivalents of it, we'll produce the amide with 2 ethyl groups off of it. And that would be an N-diethyl ethanamide. So if this was N-ethyl ethanamide, this is N-diethyl ethanamide. Now ethanamide, of course, is the IUPAC name. You could use the common name N-diethyl acetamide for the 2 ethyls being off the nitrogen. In this case, you would have gotten a CH3, CH2, NH3 plus, Cl minus, salt. And in this case, you'd get a CH3, CH2, bracket twice, NH2 positive, Cl minus. So, okay, so N-diethyl ammonium chloride. So, we can make a primary or unsubstituted amide, a secondary amide, or a tertiary amide. By reaction with acid chloride. All right, now let's modify this and look at the next derivative that we examined, and that was the anhydride reaction. How did these reactions change if we went to an anhydride? Well, suppose this chloride, we're going to change it to an X. And instead of being Cl to be an anhydride, we just make X equal to carboxylate. OC double bond O CH3. So instead of being an acid halide, the X group is an anhydride. Now this is all drawn out for you again in your notes, but it's the exact same mechanism. The only difference is we're kicking out a different leaving group. Nothing changes. If I do the exact same reaction with the exact same amines, I get the exact same product. The only thing that changes is the leaving group, and so the salts that form our chlorides here, they will be, let's write what changes in a different color. Let's use that. If I use carboxylate, if I used acetic anhydride, the anion would be that. And so I have ethyl ammonium acetate instead of ethyl ammonium chloride because I kicked out an acetate instead of a chloride. Okay, same here. So the preparation of amides from anhydrides, I could redraw the whole mechanism over again, but there is really no point when all that has changed is the nature of the leaving group. And so why don't we draw one of the reagents? Here's an X. Okay. And this time let's draw it for this one so you actually see what the X is and what it looks like in the molecule. So I'll draw the X this time. So here's the CH3C double bond O. And to be an anhydride, the X is my OC double bond O CH3. So I'm using acetic anhydride as my reagent. This is my new X. It's not chloride, it's this carboxylate. And of course it can be different carboxylates. I'm just happen to be using acetic anhydride in this case. So we can do the exact same syntheses with anhydrides. It's just the leaving group is not quite as good as chloride, so the reaction will be a little slower. Is it possible to, instead of using X as chloride or X as carboxylate for an anhydride group, could we use OCH3 for X? That is, could our X be a molecule of an ester? Well, indeed, we looked at ester reactions, and yes, the X we kick out could be an OCH3 minus. If it is, in this case, we don't use extra equivalents of the base because the methoxide that leaves is basic enough. And so the OCH3 minus that we form will grab the proton and become methanol. So in the case of ester, we're finally getting up to a leaving group that's quite basic. And so we produce the ethanamide, plus we produce methanol. So when we do the other reactions, we don't get extra ammonium salts because we only use one equivalent of the amine, and we get methanol forming. So when we use ester, the change in the mechanism is a methanol given off instead. But once again, the exact same molecule is made. And if I was to draw the reagent so that you could see it fully, that reagent would be as follows. Here we go. The X group is an OCH3. All right. So we can make amides from reaction of any of the carboxylic acid derivatives that are more reactive than amides, that have better leaving groups, and that includes acid halides, anhydrides, and esters. Okay. Now, we've looked at the chemistry of the amide bond. We've examined it in detail when we took amino acids earlier in the semester. So what we want to do right now is we want to take a look at some of the reactions of amides, some of the initial reactions. We'll continue with amide reactions a little later on. So reactions of amides. Reactions, amides. Ding. Okay. Now, amides, in terms of the reactivity, are very different from amines. They are much less basic than amine analogs. An amide has a pKb about 15 to 16, whereas the pKb for amines is approximately 3 to 5. So, and we realized this, and it was explained to us when we took amino acids, that this is due to the fact that the lone pair is less available to protonation because it's tied up in resonance with the carbonyl. In other words, there's 2 lone pairs on oxygen, 1 lone pair on nitrogen, and I can draw a resonance contributor where that lone pair is donated into a pi bond. In fact, there is evidence that there's some partial double bond character there between the carbon and nitrogen. And we get a minor contributor that has a C double bond N. And there is some evidence of hindered rotation as well. This feature was essential to the structure and biochemistry of amino acids, peptides, and enzymes. With an understanding of this lesson basicity, let's take a look at some of the initial reactions, and let's start by examining hydrolysis. After all, an amide is referred to as a carboxylic acid derivative. So let's take a look at the hydrolysis reaction of amides. Of course, we can do hydrolysis in base or acid. Let's start. I'm going to use RC double bond O. And let's use a substituted amide. We're going to react this in base, hydroxide, in the presence of water. Of course, we need a solvent. Water is a solvent. If we do this reaction, because we're in basic solution, the carboxylic acid that forms is deprotonated. And we produce free NH2CH3, methylamine. Now, the reaction is irreversible. And you'll see why in a moment. The standard mechanism is followed, nucleophilic acyl substitution, no surprises there. I'm quite comfortable with that by now. There are no protons in base, so the first step, of course, is hydroxide attack. At this stage, it is reversible. Okay, so if we add hydroxide minus hydroxide, and if we add it, we get RCO minus. No surprises here. NHCH3. Now this is the surprising part, actually, when you think about it. You were told that to be a good leaving group, you have to be a weak base. And good leaving groups are molecules that are not known to be strong bases. To reform under basic conditions, I C double bond O, look what we have to kick out in this step. We actually form an carboxylic acid, RC double bond OOH. And we kick out an NHCH3 minus. Now, under basic conditions, I'm actually surprised when I first saw this reaction that it actually happened. That you could kick out an NH minus because it's such a powerful base. It would be such a terrible leaving group. Clearly, solvation effects in water must play a role in the stabilization of this anion, as well as the fact that you're reforming the very stable carbonyl bond. But it is also possible that the hydrogen is being removed very quickly at the same time. That NH minus is not actually very far removed before it abstracts that hydrogen. Because it is such a powerful base, in the presence of the acid, you're going to get the carboxylate. This last step is irreversible. Once you get the O minus carboxylate, there is no going back. Once he grabs the proton, there's no way. You now have an anion. If the amide tried to attack the carbonyl, there's no good leaving group. You wouldn't get any reformation of the amide. So at this stage, the reaction goes fast and it becomes irreversible in base. All right. What happens in acid? What happens if we take these conditions and we play the exact same amide, but we hit it with acid in H2O? R, C, double bond O, NH, CH3. And we attack it with acid in H2O, which can be written as H plus H2O, or you could write it as H3O plus. Doesn't matter. Well, what happens, obviously, is we hydrolyze to produce carboxylic acid. And because we're an acid, the amine actually gets protonated and becomes methylammonium cation. Now, this reaction follows the standard nucleophilic process that we've covered for all these groups in acid, and that is protonation of the carbonyl followed by nucleophilic attack. Let's take a look at that. Well, the first step, of course, we're going to go plus H plus. Going back would be minus H plus. And we produce an R, C double bond O, H plus, and we have our NHCH3. And of course that is resonance stabilized with the carbocation. So I've got RCOH plus NHCH3. Don't forget there is also a resonance contributor from the nitrogen to this. I could dump the lone pair from the nitrogen, get a third resonance contributor, RCOH, which would look like this, and put the positive charge on nitrogen. Okay, so what we can do now is attack with water. Continue down. Plus H2O. Going back would be minus H2O. And if water attacks, we would get RCOH, NHCH3. Next, we can deprotonate, minus H plus. Going back would be plus H plus. Minus H plus off the protonated water will give me RCOH, OH, NHCH3. We're an acid, so we can now protonate the lone pair on nitrogen. Plus H plus. Going back's minus H plus. We'll get RCOH, OH, NHCH3, which now has an H off of it, so it's positive, a better leaving group. And so we can, if you like, actually, let's have that one go that way and draw this one that way. So what happens is we can lose our minus NH2 CH3, kick out the amine, and of course we get RCOH, OH plus. Note, because you're an acid, the amine will very quickly add a proton, plus H plus, and become NH3 CH3 plus. Okay, and now this guy is resonance stabilized. And I can draw 3 resonance contributors. And so all 3 resonance contributors get deprotonated, minus H plus. And when we do the minus H plus, we get RC double bond OH. So in acid we form carboxylic acid and the ammonium. So there's the ammonium cation and the carboxylic acid product. So there you have it. Amides are carboxylic acid derivatives because they reform carboxylic acid when hydrolyzed in water, either in basic or acidic conditions. Base is irreversible. Acid conditions is an equilibrium. However, you can imagine that this step right here, will kill the nucleophilicity of the amine. So you'd have to watch the amount of acid. If you fully protonate the ammonia, you will kill this reaction. And so typically, it's very difficult. And as you get concentrated amine, you deprotonate carboxylic acid. So typically, this reaction, once the amine's off, is not very reversible either. All right. I think that's a good place to stop. We've covered a lot of information on amides, their nomenclature, preparation, and reactions. But you should note that all of this information, the preparation and reactions, has essentially been covered in previous lectures. The reactions of acid chlorides, anhydrides, and esters was the preparation of an amide. Hydrolysis of amides was the synthesis of carboxylic acid. We've seen all these reactions before. So next Scribblecast lecture, we're going to actually look at reduction of amides and some interesting chemistry of amides. One of the aspects we're going to want to take a close look at is contrast the reduction of esters and amides. Try to make some sense out of why they behave so differently from one another. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.